Halvard?
Okay.
Han hiver han tar intervju. Hallo Helge. Hallo Erling. Er dere klare til jeg begynner å sylle opp?
Ja, jeg er klar her.
Ja, nå begynner jeg å snakke ut forsiktig. Nå går kulen fra veggen.
La de ta sakte inn.
Ta sakte inn på andre siden.
Sakte inn på andre siden, ja.
Ikke slapp du. Vent. Ta litt inn. Ta litt inn. Sånn. Ok, nå kan vi slappe.
What is calibration? Why do we do it? How do we do it? How can you do it? These are some of the questions we will be trying to answer in this program. In simple terms, calibration of a piece of hydroacoustic equipment consists in relating the electrical response of the system to a pressure excitation in the water. When the device both transmits and receives, then it is often sufficient to relate the overall transmitting power or source level and responsiveness or voltage response of the receiver to a known target or effective scattering strength. Calibration thus consists in establishing the relationship between pressure and voltage. For the present application, it is convenient to combine the incident pressure with the calibration constant K. This may be done through the particular equation relating output voltage to echo pressure. The reason is that the echo pressure depends simply on the incident pressure, the range of target scatterer from the transducer, and backscattering cross-section of that scatterer. The product of calibration constant and incident pressure can thus be expressed in terms of measurable or known quantities. The logarithm of this product is directly related to the sum of source level and voltage response. The reasons for wanting, or rather having to calibrate equipment in fisheries research is that quantitative measurements are generally impossible without it. The desire to calibrate as accurately as possible is thus apparent. The better the calibration, the more certain or less uncertain derived estimates of fish density and abundance will be. The errors that enter the echo-integration method through calibration persist throughout the process of estimating abundance. They are an unfortunate and unnecessary source of bias in the final estimate. The particular need for calibration is seen in the basic equations for echo counting and echo integration. In each of these, the computed fish density rho is directly related to a measured quantity, the count C, or echo integral I. Since these are absolute, an error in calibration will introduce an immediate error into either estimate of fish density. The motivation for calibrating is now clear. Its execution is, however, far from clear, as is witnessed by the multitude of techniques for calibrating transducers. In 1975, URIC listed 27 separate references, apparently one for each researcher or user. A cursory inspection of recent indexes of the Journal of the Acoustical Society of America shows that this number is much larger today, and that the interest in calibration is undiminished. For us, the number of practicable techniques is quite small, for transducers on fisheries vessels are rather remote, generally residing in their own housing some 4 or 5 meters beneath calm water level. In fact, if self-calibrating procedures using fish as the target are ignored, then there are only 2 kinds of techniques, those with hydrophones and those with passive targets. It has been the experience of the Institute that hydrophone calibrations are invariably questionable. If they can be believed, then the equipment performance has varied enormously and erratically with time. Measurements performed concurrently with solid metal spheres have indicated a constant performance, however, which is consistent with expectations based on field observations. That there is a difference is not too difficult to understand, for consider the nature of hydrophones and metal spheres. Hydrophones are directional devices, are extremely sensitive to their environment, age in an unknown manner, and are secondary standards, themselves requiring calibration. Solid metal spheres, when optimized, are non-directional, are insensitive to their environment, do not age, and are primary standards, requiring no other calibration. The accuracies of the two methods are similarly revealing. The accuracy of a hydrophone calibration is seldom better than 1/2 a decibel, while that with an optimal copper sphere can approach 1/100th of a decibel in principle, with 1/10 of a decibel being readily attainable in practice. As this matter of accuracy may be a sticking point, we digress to cite some literature and explain a few facts about the theoretical basis of precision calibration. The problem of sound scattering by immersed solid elastic spheres has been thoroughly studied and reported in the Journal of the Acoustical Society of America. For the present purpose, it is sufficient to cite just 3 references, those of Farren, Hickling, and Foote. Farren solved the basic problem of monochromatic scattering by a solid elastic sphere. Hickling generalized this to finite signal scattering, and Foote extended this to finite bandwidth reception of finite scattered signals. Foote also introduced a new generalized definition of backscattering cross-section. According to this, the backscattering cross-section sigma is related directly to the incident signal spectrum S, the monochromatic backscattering amplitude F of the sphere, and the receiver frequency response function H. These functions are illustrated for some important practical cases. For the common pulsed sinusoidal waveform, the signal spectrum has the characteristic sine x over x form, centered at the carrier frequency, and with a width inversely proportional to the pulse duration. The backscattering amplitude F has been computed for a copper sphere with wave number size product from 0 to 10. It is presented through the form function. The characteristic frequency response of the Simrad EK38 echo sounder is also shown. The 2 parts of the function indicate the magnitude and phase. The new operational definition shows how the backscattering cross-section or target strength of the sphere depends on the characteristics of the sphere relative to those of the immersion medium, the conditions of its insonification, and manner of echo reception. The definition incorporates the old definition, which obtains in the limits that the incident pulse duration becomes infinite or that the receiver acts as a perfect line filter. The new definition and understanding of sound scattering by immersed elastic spheres can be exploited. We can design a sphere to calibrate our equipment no matter what its state, whether in or out of tune, for arbitrary hydrographic conditions. The design generally consists in 2 parts, choice of the material and determination of the diameter. Considerations in the choice of the material include hardness, machinability, corrosion resistance to seawater, uniformity or lack of texture, knowledge of its elasticity, availability, and cheapness. For all of these requirements, copper in its electrical grade form is outstanding. This conclusion has been completely confirmed by the experience of the Institute. The diameter is generally determined with respect to criteria relating to the magnitude of desired target strength and sensitivity of this to 1 or more variables. For the 38 kilohertz echo sounders in use on Institute research vessels, it is desirable to have a target strength in the vicinity of -35 decibels. That is, with a backscattering cross-section of about 40 square centimeters. Since the Institute operates vessels from the tropics to Arctic, it is desirable that the target strength vary as little as possible with temperature. Thus, the optimization problem is formulated. Specification of both the temperature and salinity uniquely determines the density and sound speed of the immersion medium. The solution is this sphere. That is, a sphere formed of electrical grade copper that has a diameter of 60 millimeters. For the nominal operating characteristics of the 38 kilohertz echo sounder, the backscattering cross-section is about 55 square centimeters. Hence, the target strength is about minus 33.6 decibels. The goodness of the solution is seen in the relative insensitivity of target strength to temperature. The total variation is less than 0.3 of a decibel. Of course, since the hydrography can always be measured, it is possible to adjust the value of target strength to reflect the state of calibration. Variations with respect to frequency, pulse duration, and receiver characteristics have also been studied. The simple result is that the sphere target strength is rather insensitive to these, hence is acoustically robust. The 60 millimeter copper sphere has been measured many times under diverse conditions by different researchers, always with the result that its theoretical target strength is consistent to within 1/10 of a decibel. How can we exploit this accuracy in practice? The technique of passive target calibration is now reviewed with illustrations from an actual calibration exercise of the research vessel GEO-SARS. In the following description, calibration of echo sounders and echo integrators on board ocean-going research vessels is assumed. The same procedure can also be applied to the calibration of smaller scale systems with appropriate allowances for differences in the acoustic platforms and measurement configurations. 8 general tasks are enumerated. Number 1, preliminary performance testing of equipment. The preliminary performance testing consists in measurement and recording of characteristics of transducer, transmitter, and receiver. These are transducer insulation and impedance, transmitter frequency, pulse duration, and effects, time-varied gain functions, gains, bandwidths, and attenuator accuracies, and echo integrator response to a reference signal. It will be appreciated from the aim of precision calibration that the several equipment measurements should be made with accuracies consistent with the goal. This may influence the choice of test instrumentation and measurement routines. If the calibration is not being performed principally to determine how the equipment has been performing, but rather what its nominal performance should be, then adjustments in equipment parameters may be made at this stage of the calibration. The second task is rigging for sphere measurements. Ideally, the vessel is anchored in calm and sheltered water. The minimal requirement on depth is that this be sufficient for separating sphere and bottom echoes. It is desirable, moreover, to work in water as deep as possible, consistent with the need to maintain a stable platform. Both bow and stern anchoring or tying are recommended. Winches to guide and steer lines to the sphere for its centering in the echo sounder beam are affixed to the deck railing. This is done in accordance with the detailed ship drawings. One winch is placed in the transverse plane of the ship running through the transducer. The other 2 winches are placed on the opposite side of the ship, at distances necessary to forming an approximate equilateral triangle to facilitate the sphere alignment process. Each winch is provided with a long spool of 0.6 millimeter diameter monofilament nylon. This is marked with small lead weights at 5-meter intervals, beginning 10 meters from the loose end. Before beginning the sphere measurements, the lines from the two winches on the same side are drawn beneath the hull to the other winch by means of a line passed under the keel before anchoring. The appropriate sphere with a fixed loop is attached to the 3 suspension lines. It is then immersed in a solution of soap and fresh water and lifted overboard by the fastened lines without being touched. The sphere is lowered beneath the vessel to the desired depth, in the present case to about 25 meters. This is determined approximately by counting the lead marker weights on each line. The exact sphere depth is determined by several criteria. These are that the sphere be at a sufficient far-field range that the receiver not be saturated by the echo, and that the beam be uniform over small lateral ranges. The range must also be chosen to ensure a free suspension. The third task of the calibration is hydrography. While the ship is being anchored and rigged for the calibration, the hydrography can be performed. Use of a CTD sonde is convenient, for the temperature and salinity profiles can be logged automatically. The sound speed profiles and average sound speeds over possible depth intervals of sphere suspension can be computed. When the final depth is determined, detailed knowledge of the hydrography allows refinement of the nominal value of target strength. Centering of the sphere in the acoustic beam is the fourth task of the calibration. The purpose of this crucial operation is to move the immersed sphere onto the acoustic axis of the transducer, but without significant depth change. Movement of the sphere occurs by manual turning of the various winches, always singly and upon specific command by the director of this procedure, who is guided by constant observation of the echo waveform on the oscilloscope and communicates with the crew manning the winches by walkie-talkie, for example. The two principles governing the search for the beam center are first, preliminary exploration of the beam to ensure location of the sphere in the main lobe, and second, further probing to find the position of strongest echo. In the case of highly directional transducers, determination of the final axial location is made when any movement of any winch in or out cannot increase the echo amplitude. The fifth task of the calibration consists in computations for echo sounder calibration. The sphere range is measured in units of milliseconds from the echo on the oscilloscope. The range in meters is then determined from the measured echo time delay and average speed of sound from transducer to sphere. For each TVG function and pertinent combination of transmitter and pulse duration, the peak-to-peak amplitude is determined. The sphere echo level is related to this by a simple logarithmic transformation. The sum of source level and voltage response is now determined from the target strength of the calibration sphere, assuming fine adjustment for hydrography and possible deviations from nominality of the center frequency and duration of the transmit pulse. The specifying equation depends on the TVG type as shown. In these equations, R is the cutoff range for the respective TVG function, alpha is the absorption coefficient used in the TVG functions, and G is the gain or attenuator setting. The units of the various quantities are summarized in the table. Readying the equipment for echo integrator calibration is the sixth task. The echo sounder should be adjusted to that state of greatest use or interest during past or planned cruises for which the calibration is being performed. For the Simrod EK38 echo sounder, for example, the nominal operating state might be defined as shown. The selected transducer is the 30 by 30 centimeter transducer. The transmitter is external, the pulse duration 0.6 milliseconds, the TVG is 20 log R, the attenuator setting minus 20 dB, the receiver bandwidth 3 kilohertz, and the range scale 0 to 250 meters. The echo integrator is also adjusted for normal cruise operation. This might involve simulating a constant vessel speed and using an observation time corresponding to a unit sail distance. Nominal settings might be, for example, 10 knots for the speed, 6 minutes for the integration time, hence 1 nautical mile for the sailed distance. Any other settings may be used, of course, as long as these ensure a large number of integrated pings. There is one special case of possible interest, that of the historical units of millimeters of pen deflection of the Simrod QM analog echo integrator. Their use may require a specific combination of settings. In performing the integration, at least 3 integrator channels should be defined. The middle of these should fully embrace the sphere echo, and the other channels should be adjacent and of equal thickness to the central channel. 5 meters is a convenient interval in the present case. No threshold should be used. The middle channel will thus contain the sphere echo and noise, while the adjacent channels will measure the noise, including reverberation. The seventh task consists in computations for echo integrator calibration. The echo energy for each of the calibration pings is computed. The largest of these is extracted. For the simulated cruise settings, there are 288 pings, hence measurements of the echo integral. The largest echo integral is accepted if lying within a certain fraction of the mean, say 10%. If not, the integration is repeated, especially if fish or other extraneous scatterers are suspected of having been in the integration region. If this cause can be excluded, then the centering operation should be repeated and the acoustic measurements performed anew. The possibility of wind or submarine currents acting on the sphere should not be forgotten or underestimated. If necessary, the sphere may have to be recentered in the transducer beam. In any case, sooner or later, a best figure for the maximum echo energy is derived. It is now possible to use this number to intercalibrate with other echo integrators on board other research vessels. The eighth and final task of calibration is documentation of all measurements and equipment adjustments, if made, in addition to the final calibration results. Thus, measurements made under performance testing of the equipment, hydrography, and calibration of echo sounder and echo integrator should be logged. The waveform of the sphere echo, obtained by displaying the calibrated output signal on the oscilloscope should be photographed for each combination of transmitter power, pulse duration, receiver gain, and time-varied gain function of use in a cruise. This should be done whether or not the full calibration is performed for these precise conditions. Recording of the oscilloscope scale sizes will enable the particular calibration to be completed at a later date if required. Copying and distribution of the data should be routine. In addition to leaving a copy on board the vessel, the group responsible for the calibration should maintain a copy in their files. The original data sheet should be deposited in the Institute archives for long-term storage. In order to illustrate the computational side of calibration, we consider a practical example. This is calibration of a Simrod EK38 echo sounder and attached echo integrator. The system is to be calibrated for the 20 log R time-varied gain function and use of the -20 dB attenuator setting. After centering the sphere in the transducer beam, the time delay from signal transmission to echo reception is measured on the oscilloscope. This is observed to be 25.2 milliseconds. For the mean sound speed of 1466 meters per second, determined from the earlier hydrographic measurements, the sphere range is computed as 18.5 meters. The peak-to-peak voltage of the sphere echo on the oscilloscope is observed to be 3.35 volts. Thus, the voltage level is 1.5 decibels. The absorption coefficient is a constant for the particular echo sounder, namely 0.0105 decibels per meter. For the chosen 20 log R TVG function, the cutoff range is 502 meters. The reference target strength of the sphere is adjusted in accordance with a hydrography. It is -33.6 decibels. The several quantities needed for completion of the echo sounder calibration are now available. Upon compounding, the sum of source level and voltage response is found to be 144.9 decibels. In preparing the echo integrator for calibration, 3 5-meter thick channels are defined with respect to the sphere range of 18.5 meters. The center channel is defined from 17 to 22 meters, and the adjacent 5-meter channels from 12 to 17 and from 22 to 27 meters. The integration was performed over a 6-minute period at 48 pings per minute, simulating a sail distance of 1 nautical mile at 10 knots speed. The results, when expressed in the historical units of millimeters of equivalent pen deflection on the analog QM echo integrator, are that the maximum echo integral is 7356 millimeters and that the average echo integral is 6934 millimeters. The observed excursion of the maximum from the average is about 6%, which is reasonable. Further evidence for the acceptability of this number was the apparent absence of extraneous scatterers, which was confirmed by continual observation of the oscilloscope during the integration period. In addition, the peak echoes or reverberation from the adjacent channels lay in the range from 10 to 20 millimeters, thus were entirely negligible. Calibration of the integrator can now be completed by referring the peak echo energy to a 1 meter sail distance and 1 meter depth. The result is that the echo integral is 1359 millimeters. This number will facilitate both evaluation of equipment performance by comparison with earlier measurements and also intercalibration with the echo integrators of other research vessels. We may summarize our findings in a few words. Optimal copper spheres provide a fast, reliable, and accurate means of calibrating echo sounders and echo integrators. The major requirements on the part of the researcher user is to ensure care in the execution of the calibration, particularly in the definition of the operational state of the equipment and in the physical centering of the sphere in the transducer beam. Given success with these operations, ordinary calibration should be attainable with 1/10 decibel accuracy.